All right, so we're going to start with chapter 3. Okay. All right, now chapter 3 in the new textbook starts with inertial and non-inertial frames of reference. And non-inertial frames of reference. Okay. Now this has to do with circular motion, but in the old textbook this is part of chapter 2. Okay, and basically what does this mean? It means when an object is moving in any circular motion of any kind. So for example, I give you the example before. I have a car that is moving forward. My car makes a left turn, for example. Okay, as a car makes a left turn, your body, according to Newton's which law? First law, which says an object wants to stay in motion and remains in motion, right, until an outside net force acts upon it. So my body still wants to move up north, but because my car is moving to the west, I feel like there is a force that is pushing me to the right. Okay, so when I describe this, depending on how I'm looking at it, if I'm sitting in the car and I didn't know anything about forces, then I would say there is a mysterious force that is causing me to be pushed against the door. We call that a fictitious force. Okay, an example of a fictitious force on Earth is the Coriolis force, for example, the ones that cause winds to move. Okay, so Coriolis force, for example, is, I think it's Coriolis, okay, is an example of a fictitious force or a centrifugal force. In a centrifuge, people think that things are being pushed outward. They're not being pushed outward, it's just inertia. So when an object, when you're inside your vehicle and you feel like your body is being moved from one direction to another direction, like when a car accelerates, your body moves backward. When a car brakes, your body moves forward. Those are just inertia that is acting on your body. But when I'm in the car, I don't know what is causing my body to move, so therefore I give it a fictitious name. However, when we're looking at this from outside, we know that it is inertia that is causing this motion. Okay, we know that is inertia that is causing this motion, so that's why it's called inertial and non-inertial frames of reference. When the laws of inertia are obeyed, is known as an inertial frame of reference. When the laws of inertia are not obeyed, that is known as a non-inertial frame of reference. Okay, all right. So this is what we started with. Now we said in circular motion that my velocity is always going in a circle and it's constant. So one of the conditions of circular motion is your v is constant, number one. Okay, number two, what was the second condition? Yeah, radius has to be constant. So your radius is constant. Okay, your radius is constant. Now when this happens, so for example, you have an object that is moving in a circle, and then it's going from here to here, for example. Now what will happen is when we add the two or subtract the two, this is your VI, this is your VF. And what we said for vector subtraction, we said it's VF plus negative VI. VF plus negative VI. Okay, so then we would have said this was, you would have said, we would have changed the direction of this. It's going in this, or I should say, this is going in this direction. So if I add that in like here, my delta V vector would be going towards the center of the circle. And since delta V is going towards the center of the circle, okay, that means acceleration is going towards the center of the circle. And this is known as center seeking. Center seeking. Center seeking motion, which we call, what's another name for center seeking? Centripetal acceleration. Okay, this is also known as centripetal acceleration. Okay, centripetal acceleration. All right. Now, when my object is being moved outward, and which we said is caused by inertia, we call that center fleeing. And if it's center fleeing, what is it called? Centrifugal force / acceleration. Okay, so centripetal force / acceleration, centrifugal force / acceleration. Now, of course, we know centrifugal force actually does not exist. It's a fictitious force. It's caused by inertia. Okay, all right. So a few things that we need to remember. Just my formulas. Okay. So we said that since centripetal force is not a new force, centripetal force is nothing but the net force. Okay. It is made up of a combination of all the forces. Okay. So what will happen is that your FC, which equals to your F net, and the formulas are mv squared over r, which equals to 4 pi squared, what is it? mrf squared, and then 4 pi squared mr over t squared. So these are some of the formulas, and of course FC, which equals to F net, which also equals to ma centripetal, MAC. Okay, are we good with this? And then we talked about a few different scenarios that we need to talk about for chapter 3. A few things that we need to remember. So objects moving in a vertical circle. So for example, a ball at the end of a rope in a vertical circle, twirled in a vertical circle, right? Car on a ramp. Okay. Roller coasters, for example, with the inside of the loop, for example, inside of loop. Okay. Or even planes and birds, for example, moving in a circular loop. If a bird or a plane is moving in a circular loop, for example, we would say the same thing as well. We would say the same thing as well. Okay? Anything else that we've missed? Yeah? That was for the period, yes. 2 pi over v. Guess so, yeah, sure. If it's in your textbook, then it should be. I'm not sure. Okay, anything else that we've covered in chapter 3 that I'm forgetting? Okay, I can't remember anything. There is one thing I forgot from chapter 1 for period 3, which was acceleration in 2D. I didn't even talk about it. I totally forgot about it. Yes. Universal gravitation. All right. Universal gravitation, which we did, was Fg g m1 m2 over r squared. Of course, we also talked about what happens when we are Fg equals to your Fc, right? And we came up with velocity formula, which was motion of an object in a circular format. So if an object is in orbit, right? When an object is in orbit, and we came up with v equals to the square root of gm over r. This is mass of the larger body, and this is orbit, radius of orbit from center of planet. Okay? Are we good with this? We talked about this. We talked about Fg equals to small fg, and then we said it was gmm over r squared, which equals to m times g. If I'm looking for, let's say, g, I can cancel this out and you get G equals to big G m1 over r squared. We also did this as well. This was also a chapter 3. Are we good? Okay, so this was chapter 3. Now chapter 4 was energy. Energy, work, simple harmonic motion. Okay, energy, work, simple harmonic motion. We start out work equals to FD cos theta. This is a repeat of grade 11. We talked about EK equals to half mv squared. EG equals to mgh. We talked about conservation of energy. Conservation of energy, E total before equals to E total after. We talked about elastic energy, E equals to half kx squared. We talked about Fx, which equals to negative kx. This was elastic force. Okay. And then we talked about simple harmonic motion, where an object, imagine it was in a vertical thing like this, and an object is pushed inward in an ideal spring, right? We talked about an ideal spring, and a spring which does not lose NF K constant, never loses its springiness, etc., etc. And then we said that my velocity here would be my velocity here would be, okay, so basically as this object moves from one point to another, this will be your EE maximum, this will be your EK maximum, and this will be your EE maximum again. But then it will keep on moving back and forth over and over again. Okay, and we also said that this motion can be described in a couple of different ways. So one of the formulas that we got was T equals to 2 pi, what was it? M over K, square root of M over K, and F equals to 1 over 2 pi, square root of K over M. Can you just confirm that, please? Of course, T is your period. Okay, F is your frequency. We also talked about thermal energy and friction. We said work equals to F times D. But if it was friction, then they would have said that that would be Fk times D, right? Or that would be E thermal, which equals to Fk times D. Just some things to remember. When we're talking about total energy before and total energy after, make sure we take everything into account. So EE, EK, EG, for example, EE prime plus EK prime plus EG prime, and so on and so forth. Any questions? Now from chapter 2, I know I totally forgot this, or chapter 1 I should say, we didn't do acceleration in 2D. But please remember, go over acceleration 2D again. This was when an object is moving one way and then is moving another way. That VF, there at VI. Acceleration is VF minus VI